Okay, again, chapter 4, part 5, graphing other trig functions. So we graph the sine and the cosine, and those are sort of the fundamental trigonometric relationships for whatever reason. So we're going to graph the tangent and the reciprocal trig functions today, and then something called damped trig functions, which often are used to model physical phenomena. So a dampened trig function looks like this. So whatever it is, we'll call it d of x equals f of x times g of x. And this would be some algebraic function. And this would be some trig function. So like, for example, x times sine of x. And the dampening factor is just the f of x from that. So that's the only new things for this chapter. Things you haven't previously seen. And the graphs of these are pretty interesting. I'll show you, you'll see why they're used to model physical phenomena. I'll stuff you in here this morning. All right, so let's talk about the graph of the tangent of x. So tangent is the opposite over the adjacent, but what's called a trig identity is, so when you compare two trigonometric expressions that are always true with an equal sign. So one of those trigonometric identities that's going to be particularly useful to us here is the tangent of x is always equal to the sine of x over the cosine of x. So the tangent equals the sine over the cosine. That's just going to make our life a little easier to know that. So notice for this graph, the cosine of x can't be equal to 0 lest we have division by 0. So in order to graph the tangent, and a big difference for the tangent is the period is 1 pi, not 2 pi. 1 pi. So let's make a little graph here. So, and also, you remember the domain for sine and cosine was all real numbers. Here it's going to be x such that x is not equal to n over 2, I'm sorry, pi over 2 plus n pi. N is an integer. Basically, think about where cosine is 0. It's at 90 degrees, and then at 180 degrees, and then so on. So this is what forces this. So the domain is going to have asymptotes at 90 degrees, and then every 180 degrees after that, or negative 180 degrees, depending on which direction you're going. Okay, so with our graph, we want to graph two periods. So let's go negative pi. We don't have to go as far this time because the period is different. The range is going to be all real numbers. So the range is unconstrained. But remember the zeros of the cosine function pose a problem to us. And you remember they occurred here, here, and then we could go pi units and account for more of them if it were necessary. But it's not to accomplish our task. So everywhere these zeros of cosine occur, have division by zero and a vertical asymptote. All right. And the zeros of the sine will also be zeros of the tangent. Because think about this, if you've got a ratio and the numerator is zero, then the whole ratio is zero. The denominator is irrelevant. Zero divided by whatever is zero, unless it's a zero denominator. Then you have an undefined situation. So the zeros of the sine are important to us as well, and they are like so. You also have zeros here, but again, that's zero divided by zero, so undefined. So the zeros of the sine will be zeros of the tangent. And then another characteristic of the tangent is going to make graphing this easy. So the tangent is always increasing. In other words, it always goes up. So just using this information and that, get this characteristic tangent shape. Notice how it's always going upward. And let's use our calculator to confirm our graph here. Right. So we want tangent x. And we want to go from negative pi to pi. And we want to go from, say, negative 2 to 2. All right, so the vertical lines are not part of the graph. That's a mathematical artifact. That's because the TI calculator is imperfect. It models asymptotes imperfectly. If you've got a newer version, it won't show up. And in fact, I really don't see anybody with the old 83s anymore. I really need to update my emulator here. It's just a hassle to do so because I've got to upload the ROM to the computer and all that. But anyway, so tangent of x would look like this. Questions about this? All right, this is just the same thing, so I'll delete it. That way we don't have a redundancy in the notes. So this is the properties of the tangent function. Nothing apart from what you've already written down is necessary. Know that it's in your book, and if you need to see it, feel free to look. This is several periods, 3 periods instead of 2. The period is the distance between two asymptotes, which is pi, as I mentioned. Okay, so let's talk about y equals tangent over 3. Tangent x over 3. So we want to do the vertical asymptotes and sketch the graph. All right, so we've got a period change here. Remember that when we have a b parameter, just like in the sinusoid, it's going to affect our period, and it's going to affect it in the same way. So the period of this modified tangent function is going to be the original period divided by the absolute value of that b parameter, which in this case is going to be 3 pi. So the graph needs to go from negative 3 pi to positive 3 pi. And it will have the same shape. Finding all the asymptotes, we just need to say they're going to be at x equals 3 pi over 2 plus 3 pi n, where n is an element of the integers. As usual, we'll use a calculator to check ourselves here. You never know, people make mistakes. So tangent of x over 3, and I need to change my window to go from negative 3 pi to 3 pi. Yep, we got it right, looks like. That's a good habit to get into, though, especially on a quiz or a test. You know, a homework problem is low stakes. You'll lose 5 or 10 points on a homework, which is a negligible difference in your overall grade. But, you know, if you bomb one on a test, there'll be 3 or 4 tangent questions on the test. You miss all those, you probably failed. So, worth double checking on a quiz or a test. Quiz is due tonight, by the way. Really should have done that before. But for those of you that waited till the last minute, it is due tonight, so don't wait any longer. All right. Locate the vertical asymptotes of y equals tangent of 4x. So I don't know that you're really comfortable enough to do this one by yourself just yet, so let's do it together. Tangent of 4x. So the period is going to be the original period divided by that b parameter. Everybody with me on this? And because the tangent function is the vertical asymptotes are going to be equidistant from the origin by default. In other words, the origin is the middle of a period. I can't just go pi over 4 units this way. I need to go half as far, which is pi over 8. See how together that would be pi over 4. So the asymptotes are going to occur at x equals pi over 8, and then plus the period, which is pi over 4, times n, where n is any integer. So half the period plus the whole period times n, where n is an integer. That's going to describe every asymptote possible. These are kind of tricky. So make sure you give that a little bit of study time before we have the test on Wednesday. So our last week, hybrid, kind of relieved, to be honest. Feels like letting out a breath. A weird couple months.
What is the little subscript next to it?
N is an element of z.
No, the
comma.
okay.
Typically, if you have multiple mathematical expressions in a given equality symbol, you separate one comma sign. But good question. Sure you weren't the only one wondering about this mysterious mark. That's a comma. Okay, so sketch the graph of the tangent of 4x. Well, we know from that, this is the same one from the previous example. The period is pi over 4. Notice how I'm just doing the same graph over and over again and re-indexing the x values? That makes it the simplest thing in the world. So if you get your x values right, you can do that. How many asymptotes with a tangent have total? If I were to make this graph extend further and further and further, well, there'd be an infinite. Go on every period from the previous, there would be another to infinity. So if I go pi over 4 units, there's another, and so on and so on and so on, forever till the end of time. Whatever the period is for the specific function under consideration. It's not always this, it's whatever the period. Okay, locate the vertical asymptotes and sketch the graph of y equals negative tangent x over 4. So we've got two transformations taking place now. We've got a flip over the x, and we've got a b value equal to 1/4, and so our period is going to be pi divided by 1/4, which is 4 pi. So remember how I said the tangent was always increasing. So if we flip it over the x, that's going to be always decreasing. That'll be the only difference that manifests. So let's go negative 4 pi. So 4 pi. Right, so remember, we're always decreasing this time. I'll double check us with the calculator. So we need negative tangent of x over 4. The window needs to go from negative 4 pi to 4 pi. Like I said, double check. It's easy to get these things mixed up in your head. Even for me, and I'm a very visual person. Graphs are what make most sense to me in all of mathematics. So now we've got a phase shift. So this is where it gets kind of funky. So sketching these by hand will be considerably harder once you have a phase shift. At least they are for me. So notice we have this C parameter. So we've got this, which is going to flip us over the x. And we've got this, which is going to move us pi over 2 units to the left. We don't have a b parameter, thank goodness. Make our life even harder. So we'll just go from negative pi to pi. That'll be 2 periods. So normally, the first asymptote I would graph would be here. But remember, we're shifted pi over 2 units left. So I go that far left and I'm here. Normally, the second one I would graph would be here. That's shifted. And then the one that normally would be off the graph, shifted here. And we're flipped over the x, so we're always going downward. Going downward. So that one looks like that. Let's, as usual, double check ourselves. Negative tangent of x plus pi divided by 2. Remember, you must be in radians mode when you're graphing, or you're going to have all sorts of issues. We want to go from negative pi to pi. All right. Questions about that one? Okay. So modifications of the tangent function work effectively the same way as the sine and the cosine. The big difference is the original period is pi in this case. So when we modify the period, pi is our numerator. I think we're good on those. So let's talk about the other trig functions, the reciprocal functions. We'll begin with cosecant of x. And remember, that is the reciprocal of sine of x. So the domain is going to be x such that sine of x is not equal to 0. So we can't have the zeros of sine. The range is going to be like the range of the sine function turned inside out. So it's negative infinity to negative 1, union with 1 to infinity. So this is just like the sine function if we turned it inside out. So let's graph it. We're going to use our knowledge of the sine function to make our life easier here. The period is 2 pi, just like the sine itself. So we're going to dot in the sine. Use the sine as a guide for the cosecant. All right, so sine includes the origin, and it has zeros at every multiple of pi. Sine of pi over 2 is 1, negative 1. Consistent. Okay, so this point, this one. We're just dotting in the sine as a guide, cosecant. Not actually part of the graph, just going to help us. So the cosecant itself.
Mr. Salyer?
Yes.
Do you have Allie Hensley?
I do not.
Is she absent today?
Yes.
Okay, thank you.
You're welcome. So all these maxes and mins are going to be shared by the cosecant and the sine. And all the zeros of the sine are going to be asymptotes. And then around those asymptotes, going to be these little parabolic shapes, again, just as though we turn the sine inside out. That is the cosecant. Let's use our calculator to confirm our graph here. So let's see, I want 1 over the sine, because this calculator doesn't have a cosecant button. And I want the window to go from negative 2 pi to pi. And let's give it a little more y, negative 3 to 3 would be good. You see the relationship with the sine? So if I were to graph the sine here, that relationship might be a little more obvious. See what I mean here? And you can use the sine to understand the cosecant. That keeps you from having to memorize this complicated graph. You just remember this dotted line. The rest of it should be obvious. All right, now we've got the now we've got the secant of x. And that is 1 over the cosine of x. So again, the domain is going to be x such that cosine of x is not equal to 0. And on that first one, I went ahead and changed this to pi over 2 plus n pi, where n is an element of the integers. But you guys kind of looked at me weird when I did that, so I think maybe this might make more sense. This means the same thing. These are the zeros of cosine. The range is the same as this cosecant. So it's going to be y such that y is less than or equal to negative 1, or y is greater than or equal to positive 1. I used interval notation last time, but this means the same thing. Good for you to see both. As the year goes on, the coffee gets stronger. Eventually, I'll be snorting meth. Just kidding, though. Okay, so let's sketch our axes here. Once again, negative 2 pi to 2 pi. The period is 2 pi. And we're going to have y equal to the secant of x, where x is some angle. So this time we're going to dot in the cosine to help us. So I'm going to mark the zeros of the cosine. Remember they were here. And then some other key points from the cosine. Cosine, for me, is best done kind of inside out. So let's dot it in here. There's the cosine of x. And the same as before, all the zeros are going to be vertical asymptotes, or VAs. And then the maxes and mins are going to be points shared between the cosine and the secant. And it's just going to be these parabolic shapes that represent sort of inside out cosine. Now you've got a partial one on each end if you only graph two periods, so that could be a little weird. We've already got our calculator set up here, so you don't need to change the window, just change that to cosine. And I'll change, I'll also graph the cosine so we can help you see that relationship. First it'll graph the secant, which is what you see here. Then it'll graph the cosine, and hopefully that helps you understand the relationship between those two functions. Okay, any questions about that? All right, let's do it. This is a redundancy again. Last one, cotangents. So remember that this is equal to 1 over the tangent of x. And remember how the tangent was the sine over the cosine? So we could also describe this as the cosine over the sine. We want to. So either of these represent a true identity when compared to cotangent. The period is pi. The domain is going to be x such that sine of x is not equal to 0. It can't be a 0 for the sine unless we get division by 0. The range is going to be y such that y is a real number. In other words, all values are in the range. And I think that's all the information we need to get started. Oh, it is always decreasing by default. So that'll help us. So to find our zeros, we'll go from negative pi to pi. To find our zeros for the sine function, remember the origin is 1, and then every pi units in either direction. So we have a vertical asymptote for our cotangent here, a vertical asymptote here, vertical asymptote here. Now, always decreasing, so the same kind of funky shape as the tangent, but always going downward instead of upward. So I'll graph it on the calculator here. Oh yeah, baby. Like me some trig graphs. Okay, questions about anything we've talked about so far? So if we graph the trig function and we fiddled around with some parametric changes, transformations of the trig function, and then I showed you the cosecant, the secant, and the cotangent. All right. You should be masters of all those things by now. So your book has these pages where they list all the properties. Feel free to review that. I won't test this information directly, but it will be an indirect portion of several test questions. Let's see. Say again? 272. So, and these exist for virtually all the trig functions somewhere in the book. Feel free to review those if you don't feel comfortable with them just yet. So let's sketch the graph of the modified cotangent here. So we've got y equals the cotangent of 2x. So I've got only one parameter here. I've got a b value. So Colby, tell me how that would change my graph. Now that would be a phase shift or a C. B value does something else. Very good. Changes the period. In what way would it change the period? So my period originally is pi. What's it going to be now? Very good. Pi divided by the absolute value of b, which is pi over 2. So the only thing different is the indexing. Remember, you can just do the same graph over and over again if you reindex your x-axis appropriately. So the vertical asymptotes are going to be pi over 2 n, where n is an element of the integers. So x equals pi over 2n, where n is an element of the integers. Yep. Tend to go through these graphical lessons pretty fast to make sure to see any questions you have as we go.
Whenever we go back to like regular school, is there still gonna be students that are like virtual and stay at home, or is everybody coming back?
Yes. So Mackenzie's question was, when we go to off the hybrid schedule, will there still be remote learners? The answer is yes. So parents would still have the option to opt out of school entirely. So the completely remote students will still be completely remote. I don't know if they're going to give them the option to change, because originally they said if you make that decision, it's for the semester. But the school may back off from that. I don't know about that. But yes, you will have some remote learners. And in fact, we've got some in this class. So there will be students still online only. Good question. All right. So here's one for you. See if you can tell me where the vertical asymptotes, you don't have to sketch the graph or anything. Just tell me where the vertical asymptotes of this function are. The VAs. All right, so the first thing you need to do is figure out the period. Macy, tell me what you got for the period of this. Say again. Very good. And then, Clay, where did you think the vertical asymptotes might lie?
Just looking at the graph that we just did, I would assume it's negative pi over 2 and 0, and then pi over 2.
Good. So a way to describe all of them is going to be this.
X equals pi over 2 times n.
Yep, where n is an element of the integers. So you're right, those were the ones that would be on the graph. But to find all of them, we need an expression like this. Okay, so algebraically, to describe everyone forever, now we can't just make a finite list. We need something like this. All right, so sketching the graph is pretty trivial. We do have one little thing here. This 1/2 is going to be a vertical compression. So it's going to be slightly closer to the x-axis than the other. So it's just going to be flatter around the axis. So if we go from negative pi over 2 to pi over 2, it's here. Our asymptotes we previously described, and just, like I said, flatter towards the x-axis. That vertical compression will have that effect. We'll just graph it here and see what we look like. So 1/2 cotangent of 2x. Okay, I think that's right. Window, negative pi over 2. And then pi over 2. Yeah, so this vertical compression is a pretty subtle change in the graph, but it is there. If I take that away, I'll let you know the difference. You know, it's a little further away from the x-axis without the vertical stretch or vertical compression. All right, so properties of the cosecant and secant function. Again, this exhaustive list of characteristics, and I won't directly hold you responsible for this information, but there will be questions regarding the cosecant and secant, so it'll be worth your time to understand them. I showed you everything I would test directly on. So let's sketch some transformations of the cosecant and secant. I've got the negative secant of 2x, so this is going to flip over the x, and this is going to change my period to be 2 pi over 2, or just pi. So what previously happened in between negative 2 pi and 2 pi is now going to happen between negative pi and pi. We use the calculator to graph this one, because once we get into these more complex expressions, it's pretty time consuming. So this is 1 over the cosine. One good thing about having these old calculators is you really understand the relationship between the reciprocal functions and the original trig functions, because you have to put them into this format. And we want to go from negative pi to pi. So re-indexed to negative pi to pi and flipped over from that original formulation. Stop me if you have a question. Okay. So now let's do cosecant of x plus pi over 3. Now these funky phase shifts, these are the ones you got to be really wary of because they are the least intuitive transformation, at least from my point of view. The ones that will really, you won't be able to visualize it very well. So I'm going to rewrite this in a way that allows me to put it in the calculator, which is 1 divided by the sine of that same argument. Yeah, the only thing taking place here is we've got pi over 3 leftward, but that's not an amount that's on the unit circle, so it's just going to be weird. It's going to make the graph look weird too. Period is the same. The period's unchanged. So we want to go from negative 2 pi, and we want to change this to be 1 divided by the sine of x plus pi divided by 3. And if we graph, so see how kind of asymmetric and weird that gets when you have a phase shift? It would be difficult for me to visualize that just based on that information. Okay. Now, what about locating the vertical asymptotes? Well, remember that the sine of that argument can't be 0. So where is the sine of x minus pi over 2 0? Well, normally 0 is a 0 plus pi, but here we're going to shift all of that leftward pi over 2. So it's going to work out to be pi over 2 plus n pi, where n is an element of the integers. Those are the values of x that are going to cause that to be 0. We'll graph it just to be sure, just the sine part rather. So the sine of x minus pi over 2. So these phase shifts can be tricky. And we're already set to go from negative 2 pi. Yep, that looks like it happens at pi over 2. We'll just trace and go pi divided by 2. We see that's a 0. And then we'll do one more just to check. 3 pi divided by 2. Yep, that's another 0. So this is right. And then they're going to ask us to sketch it in part B, but we'll get to that in a second. Questions? Yes, ma'am.
Would it be moving to the right? Because the last one it was adding time to that one.
The graph moves to the right, but the symmetry around the origin, you could go in any direction. So the ends can be positive or negative. So really it just moves the period's beginning point, I think is a better way to understand it. This would technically shift the graph to the right, but you could also interpret it as a leftward shift. You know, if you were willing to say that each period is equal. Good question. Yes, sir.
Would you go over again how you got the vertical asymptotes pi over 2 plus n pi?
Yeah, I just thought about what values of x would make this expression equal to 0. So I knew that 0 is normally a 0 of pi. So if I plug in pi over 2 minus pi over 2, that's 0. So that would be a violation of this, create a vertical asymptote. So I started there. And then I added pi units because that's how long it takes to get back to 0. Good question. These get complicated, especially with secant cosecant. It's not very intuitive. You just have to mess with them some. But good questions, you guys. All right, now let's graph it. And again, we'll use the handy dandy calculator to help us here. So 1 divided by the sine of x minus pi over 2. Yeah. And I want to go from negative 2 pi to 2 pi, so that's where I'm at. So that is the cosecant shifted pi over 2 units to the right. Okay. Questions about anything so far? All right, some complicated stuff. Now let's talk about this dampened trig function business. These are kind of fun. They're really interesting graphs, as I mentioned earlier. So we're going to talk about y equals x over 2 times sine of x. So our f of x, or the dampening factor, is x over 2. And then our g of x, the trig function, is sine of x. And a good way to get a sketch of these is to graph both the positive and negative f of x. So we're going to graph f of x and negative f of x. So let's see. Let's go from negative 10, 10, 5, negative 5. Okay, so x over 2 is just going to start at the origin and has a slope of 1/2. So over 2 up 1. So over 5 up 2.5. Over 10 up 5. Back 5 down 2.5. Back 10 down 5. There's f of x. And then the negative f of x is just going to have the opposite slope. So we dot them in here. A little irregular there. Let me fix that. Asymmetry. So what the trig function is going to do, and again, this is going to be a pretty rough sketch. It's going to kind of bounce back and forth here. So it's going to bounce. It'll be more regular. Let me graph it, and then we'll have a better idea of what exactly it looks like between those two asymptotes. So let's graph, first of all, x divided by 2. Then negative x divided by 2. And we want to go standard window, so I'm going to zoom 6. So that's what we've got going there. And now if I graph x divided by 2 times the sine of x. You get that? Something like this. Dampened trig function. And if I zoom way out, it really looks interesting. So let's give it a lot of x. So if I go from like negative 40 to 40, and then I'll need half that much, so negative 20, 20. See how that sort of like, looks like the propagation of a sound wave maybe or something, because it spreads out, or a light cone. How light cones work? Well, light cone refers to something that's inside the time bubble of an event. Let's say the sun winked out of existence right now. We wouldn't know it. We're outside of that against light cone. It takes 8 minutes for the sun's light to reach us. So for 8 minutes, we would be blissfully unaware. And then we would be in its light cone and observe the event. There are events taking place on the other side of the universe that we have no idea about. Now, when you look up into the night sky, you're actually looking into the distant past. Many of those stars are already dead and gone by supernova or some other mechanism. And yet they still burn on from our point of view as we're looking at their something that could be modeled by this interesting function. Okay, so I think that's pretty much everything we need to worry about. Yeah. So what I'd like for you guys to do is page 277, 1 through 4 all, and then selected problems 17, 18, 29, 30, and 35. All right.